So this year's speaker is Professor Brian Schmidt, and the title is The Accelerating Universe. Before I go and introduce him, I want to thank on behalf of the board of the Koninklijke Natuurkundig Genootschap, the people from the Studium Generale who've done an excellent job in helping us organize this evening. So very many thanks to the people from the Studium Generale. So here is our speaker and the poster that we had. Brian Schmidt was born in 1967 in Montana in the United States. At the age of 13 he moved to Anchorage, Alaska, where he grew up for the rest of his teenage years. He went to study physics and astronomy first in Arizona and later at Harvard, where he got his PhD in 1993 under the direction of a very well-known astronomer, Bob Kirshner, who was and still is a leading expert on supernovae. Brian's thesis was on type 2 supernovae and the Hubble constant, and the lecture that we have tonight is in more or less the same area. It's a different kind of supernova. It's not the Hubble constant, but a change of the Hubble constant. But in any case, it goes back to his thesis. After a short period as a postdoc at the Center for Astrophysics in Cambridge, Massachusetts, Brian moved to the Mount Stromlo Observatory at the Research School for Astronomy and Astrophysics of the Australian National University in Canberra, in Australia, and he has been at that place since then. He has become a leader of a team that was called the High Redshift or High Z Supernova Search Team, which was founded at about the time he moved to Australia. And the aim of that team was to use another type of supernova, type 1a supernovae, to test the expansion of the universe and to map the expected deceleration of the expansion because of gravity. And that of course led to the work that he did eventually that gave him the Nobel Prize. He is now in charge of a new instrument, SkyMapper, a new telescope, or robotic survey telescope at a different observatory of the same organization, Exciting Spring in Australia, that will make a complete survey of the southern sky. As a matter of fact, Kapteyn, one of his first work also to measure plates to make a complete survey of the brighter stars in the southern hemisphere, so that's very, very appropriate. Brian has another hobby, which I don't think comes from living in Alaska, but he and his wife operate a winery in Canberra. Once a year there is a Saturday when there is a big party and all the staff and students and postdocs of Mount Stromlo Observatory move out to pick grapes for him. I think you still do that, Brian, which is a very big thing, but it's also a very, very, very good winery. So, he did get the Nobel Prize for Physics in 2011, together with two colleagues, Saul Perlmutter and Adam Rees. I've given here you the formal quotation by the Nobel Committee for the discovery of the accelerating expansion of the universe through observations of distant supernovae. Of course, he has many other distinctions, but I don't think I should take much time to list them. And I'm just very happy that I can give the floor to Brian. We're proud and very glad that you are here and honored that you will be here tonight, Brian. And I give you the floor to deliver the Kapteyn Lecture. Thank you very much.
Excellent. Thank you, everyone, especially those of you on the floor. I hope to be entertaining so that your backside, which I'm sure will fall asleep in the next 45 minutes, that pain is worth the gain of being here. It is a great honor to be here. Groningen is a real center of world astronomy, and indeed I see it as being, the Kapteyn Institute is really being sort of the sister or brother institution to my own institution, Mount Stromlo. And we've had many astronomers over the years, including Pete, come and visit us on a regular basis, and we love to come here as well. Pete, especially for me, has always been an inspiration, and indeed he was one of the people who wrote letters of recommendation for me to get the job that I effectively have now, and so that was highly appreciated. So I get to I'm paying him back, but it's great to be able to give a talk to such a full crowd. So today I'm going to talk about the accelerating universe, and to understand the accelerating universe, you really need to understand the universe. So it's really going to be a discussion of pretty much the cosmos from beginning until end. Now, I realize we come from a variety of backgrounds, so we're going to start at the beginning just to get a sense. And I want to first give us a tour of the universe. And we're going to do this tour to sort of get a sense of our place in the universe. So we're going to need some of this knowledge later on. So let's first start with how we do tours of the universe. We use the speed of light. Why do we use the speed of light? Well, because it's a useful way of getting distances from quite nearby, like the moon, to things across the universe in the form of time, where you can understand seconds and billions of years due to that shared history we have of Earth and dinosaurs and everything else. So the speed of light is very fast. It's 300,000 kilometers per second, but it's not infinite. It's finite. And the fact that light can only travel 300,000 kilometers per second, and nothing can travel faster than that, provides a certain set of bounds to the universe, which end up with quite odd ramifications that we'll talk about today. So let's look out into the universe that we know and love. We'll start off with the Earth-Moon system. So the moon is roughly 1.5 light seconds in distance. And so, to put that in perspective, when Neil Armstrong took his one small step for humanity, that signal, in the form of a radio wave, traveled from the moon to Earth. It turns out it was captured by a radio telescope just down the road from Mount Stromlo, about 20 kilometers away, and broadcast around the world. But we found out about it 1.5 seconds after it actually occurred, because that's how far away the moon is. And the moon, of course, is the nearest thing astronomical to us in the sky. If we go a little bit further afield, you've got something like the sun. Now, the sun is bigger than the Earth-Moon system by a lot. It's 5 seconds across in terms of the speed of light. But of course, the reason why the sun looks about the same size as the moon in the sky is because the sun is a lot further away. It's roughly 8 light minutes in distance. Within our own solar system, we can go further out. We can, for example, look at the edge of the solar system, which extends out to many light hours, or even to about maybe 1/3 of a light year when you go out to the outer part of the solar system where comets form. And then we can go on through space to the nearest stellar system to our own. That is a stellar system that I see pretty much every night before I go to bed in Australia, and it's called Alpha Centauri. And Alpha Centauri is one of the brightest stars of the southern sky, and we use it in Australia to point to the Southern Cross, although the Southern Cross is pretty obvious in its own right, so maybe I use the Southern Cross to point to Alpha Centauri. But Alpha Centauri is 4.3 light years in distance. It is the nearest stellar system to our own sun. It's actually 3 stars, 2 quite close to each other. Both those stars are roughly the same mass as our own sun, roughly the same size. So to put it in perspective, if we think of our sun being a football here in Groningen, and you ask yourself, if the sun were a football here in Groningen, where would the sun, our sun, as another as Alpha Centauri as another football, where would it be? And if you think about the scales, it would be back in Canberra, in Australia, where I'm from. Through the Earth, that's the scale. The nearest star to our own is a football separated on the other side of the planet. And to think that this is in one of the most exciting places in the universe, a galaxy, our galaxy, the Milky Way. Now, this is a picture of the Milky Way. This is taken in the infrared by a couple telescopes, one in the north and one in the south. You can't actually see the entire sky from any place on Earth. The Earth gets in the way. But if you look at it in a nice clear night, this is what it looks like. There's 100 billion stars. 100 billion stars, not dissimilar to our sun in the Milky Way. And they form this kind of big pancake-like, or 2 eggs back to front. And if you also take that picture, you'll see there's 2 little galaxies The Large and Small Magellanic Cloud, again, I can see them before I go to bed almost every night. And in a nice dark location, when you look at the Large Magellanic Cloud, it really does look like a galaxy. You can sort of see the spiral arms. We call them dwarf irregulars. We don't have particularly politically correct names for galaxies, it turns out. The Large Magellanic Cloud is a mere 10 billion stars. The Small Magellanic Cloud, only 1 billion stars. And those two galaxies are satellites. They're moons of our own Milky Way. And our Milky Way is roughly about 100,000 light years across. And the distance to the Large Magellanic Cloud is about 185,000 light years in distance. But of course, that's just our own little part of the universe. We can move on and we can look across the entire sky. And with modern equipment, we can do that better and better. And so if we look at a tiny piece of sky, in this case about 1/13 millionth of the sky, that's how big it is relative to the moon, and we stare at it with the Hubble Space Telescope, the most sensitive telescope that we have today at optical wavelengths, this is what we see. We see a field of galaxies. Each one of these galaxies, not dissimilar to our own, with 100 billion stars. There's roughly 20,000 galaxies in this image. But we're looking back in time now, not hundreds of thousands of years, but 12 billion years, long before the Earth was formed. Now, we astronomers like to postulate, what does this mean? So one thing people always ask me is there life outside, beyond the Earth? And the answer is, I don't know. But I do know that there's roughly 160 billion galaxies in the visible universe. That is, if you just take how many galaxies were in that image and multiply how many images you need in the sky, you get about 160 billion. And each one of those galaxies has about 100 billion stars each. And one of the things we've realized is that almost every star has a planet. Now, probably only 10% of those planets, 10% of those systems have planets that we would say have the potential to have habitable life. But that's about how many stars there are in the visible universe. That's a lot of zeros. And we can compare that, for example, to the number of grains of sand on Earth. Now, it turns out people don't really know how many grains of sand there are on Earth. We actually know how many planets there are in the universe better than how many grains of sand there are on Earth. But there are more chances for planets that habit life in the universe than there are grains of sand on the Earth by many orders of magnitude. So I don't know if life is beyond the Earth, but I do know that there's a lot of chances for it. And one of the amazing things that we're going to be able to do over the coming decades is actually go and ask that question, because we have the technology not just to discover planets, but in the next 10 years with future telescopes, and I'll tell you a little bit about those later on, we'll actually have the ability to look for things like the signatures of life around the nearest planets. So we astronomers are always liking to build bigger and better telescopes. And they are because they allow us to see further and further and fainter. But at some point, we run out of time. Because if we look back 13.8 billion years, this is what we see. And this is an image not taken with the Hubble Space Telescope in optical light. It's an image taken in microwaves with a telescope from space, known as the Planck satellite, that the European Space Agency launched a few years ago. And what you're looking here are not at stars and not at galaxies, but rather at the universe when it was hot, roughly 3,000 degrees centigrade. At a time when there were no stars and galaxies because it was too hot, they hadn't formed yet. A time, as we know now, about 380,000 years after what we call the Big Bang. So, how do we know all this? Well, we have, over the past century, come together through generation of astronomers to understand how the universe works. And the field of cosmology, which is understanding how the universe works, really got its start in around 1916 or 1917. So the first thing, or one of the things that happened that year, was that astronomers were out looking at the nearest stars and taking spectra. That's where you spread the light out into the colors of the rainbow. And every chemical element has a certain chemical signature that shows up in its spectrum, a series of colors that it emits or absorbs. And one of the things they looked at were these things known as nebulae. Now, we didn't know what nebulae were in 1916, but one of the things that this man, Vesto Melvin Slifer, whose family actually gave me a scholarship to attend the University of Arizona, I sadly had no idea who he was. I didn't realize he would become one of my heroes. And he's someone that almost no one knows, but he's incredibly important. Vesto Melvin Slifer looked at the spectra of these nebulae and realized they looked a lot like stars, with a difference. The light was stretched redward compared to, for example, the sun, so that the lines of, for example, sodium didn't end up where they're supposed to be. They were red where they would be in a star like the sun. And he knew what that could be caused by. There's the effect known as the Doppler shift, which we all hear when we see a car go by with police go by with a siren. In this case, an Australian one, where as the object's coming towards you, the pitch is raised because the sound waves are compressed. As it goes past, they're stretched and the pitch is lowered. Light is, of course, a wave. It's a little bit different type of wave than sound, but the same basic effect is present. So when you see the fact that the light is stretched redward, it indicates that these nebulae were moving away from us. And that presented quite a mystery. In 1916, Slifer realized that almost all these nebulae were moving away from us, and some at quite high speeds, about 1,500 kilometers per second. And since the time of, the Copernican revolution, we have this idea that we should not be a special place in the universe. And yet these observations in 1916 seem to indicate we were a special place in the universe. We were a place where everything was moving away. So you can think of us as, the very least, as being a very unpopular part of the universe. And people couldn't really figure out what was going on. It was a conundrum of the day. How did we sort this out? Well, it was sorted out by measuring distances. Now, measuring distances in astronomy has always been hard. And the reason is you can't just lay down a ruler between us and the nearest star or galaxy. Rather, we have to rely on how things appear. Now, of course, the further away something is, the fainter it appears, or the smaller it appears. That latter statement is not exactly true in our universe. I won't talk too much about it, but things certainly, the further away they are, the fainter they appear. So you can imagine if you see something, a light bulb, and you see that it's fainter one time than another, the fainter one is further away. And you use the inverse square law, that is that the brightness of an object varies as the square of the distance, and you can calculate distances that way. So that's what Edwin Hubble did in 1929. He went out and looked at all those galaxies, and he had access to the largest telescope of the day, the Hooker 100-inch telescope, and he looked at how bright the stars appeared in those galaxies that Slifer observed. And what we found was something remarkable. The faster the galaxy was moving away, the fainter its stars were. And he showed this to the world in 1929. Here's his data. And one thing I always love to remind people is that the great conclusions and understandings that we have in humanity boil down to scrappy little diagrams like this. So we plotted brighter stars and fainter stars versus what their redshift, their Doppler shift appeared to be. And there was a trend. The brighter stars, objects with brighter stars, thereby closer, were not moving very fast. The objects that had fainter stars were moving very quickly. And from this, he announced to the world in 1929 that this meant that the universe was expanding. So why did he say that? Well, I'll give you a quick little description, or a toy model to give you a sense of it. Imagine I have a universe which, thanks to the wonders of my computer, I can expand. So I've expanded the universe, played God, and now I'm going to overlay before and after, and what do we see? I take from my reference point in the center a before and after, and the nearby objects have moved a little bit. If I was measuring their velocity, it would be low. The distant objects, they've moved a lot. If I was measuring their velocity, it would be high. If I expand the universe, I see that the further away an object is, the faster it's moving. And it doesn't matter where I am in the universe, no matter where I choose as my reference point, I see the same thing. The Copernican ideal is preserved, and all you have to do is accept the fact that the universe is expanding. Well, it turns out we had other reasons to believe that the universe might be expanding. We just hadn't realized them yet. And they came from none other than Albert Einstein. In 1907, Albert Einstein had what he described as his greatest thought ever. Much bigger than E equals mc squared. Rather, it was this very subtle idea, which is that gravity, the acceleration due to gravity, and the acceleration just due to moving faster were equivalent. They were not physically different. There were no way to separate them. In other words, imagine you're in a rocket ship with no windows. You can't tell if you're being accelerated by 9.8 meters per second squared, or if you're just sitting in that rocket ship sitting on Earth's surface, being accelerated by gravity by 9.8 meters per second squared. A small little thought that took Einstein 8.5 years to solve, because it turned out to require a huge amount of mathematics, and it required that space itself be curved. So it predicted curved space, and it allowed Einstein, with this theory, to go through for the first time, and I should say it was tested by looking, for example, the fact that it predicted curved space. You could look at an eclipse, and here's two pictures taken in 1919 of an eclipse. Don't mind the fact that the first image it's cloudy and there are no stars, and the second image the stars look like donuts because the images were out of focus. Sir Alfred Eddington, astronomer in Cambridge, used this to confirm Einstein's theory of general relativity, predicted correctly the curvature of space. It is interesting to note that if you go through and use modern techniques to analyze the picture on the right, the one you can, it's not possible to actually make that claim. The data are not good enough. But Eddington gets a lot of points for getting the right answer for the wrong reason. The work actually came in 1922 from another eclipse, which was definitively showed won't get to acceleration yet, that the curvature of space as predicted by Einstein was present. And this also allowed Einstein to do something that Newton never could do, which is to say, imagine I have a universe that goes on without end. How does gravity work in that universe? And so he was able to solve that. De Sitter also, who you heard earlier, did the first solution. His first solution of general relativity was for a universe that was completely empty. And Einstein ridiculed De Sitter, asking him why he would bother wasting his time on such a, trivial piece of physics. Turned out there was a lot in that piece of physics, as Einstein soon figured out, because when Einstein did it, he had a problem. The solutions to the universe were dynamic, and he didn't really know what that meant. He knew that the universe's scale would be changing. That is, the universe would be expanding or contracting. But they didn't think of it that way in 1916 and 1917 when they were doing this work. Instead, what Einstein did is he said, well, the universe looks static to me, and if I look at my equations very carefully, I can add something to it. A constant of nature, which we think now as being energy that is part of the fabric of space itself. And it turns out in his equations of general relativity, this energy that's part of space makes gravity push rather than pull. And so his idea was that he would add enough of this energy to space so that it could counteract all of the gravity in the universe that's pulling and make the universe static. He was so sure his equations must be right, he felt the need to add what is effectively a fudge factor to his equations. Now, it turned out that if a butterfly flapped its wings somewhere in the universe would either start to expand or contract. That is, the solutions were unstable mathematically. So this ended up not being a solution for Einstein. But of course, this was 12 years before Hubble made the discovery that the universe was expanding. And so later on in life, he was quoted as saying, "This was my greatest blunder." I actually think the direct quote was that I was acting like a donkey when I was putting out the cosmological constant. All right, so within the framework of general relativity, there's a little bit of a difference. When you look at a distant object, light as it travels through space is traveling through space which is expanding. And so the light, which is a wave, gets stretched by the expansion of space. It's not so much that those objects are moving away from us, rather that space between us is being created, stretching the light. That's a subtle difference, but it's an important difference in that you don't have to worry about solving for things like kinetic energy and stuff between these. That's not part of the deal within general relativity. Now imagine a universe which is expanding. Let's run it in reverse. What happens? Things get closer and closer and closer, and you naturally come to the idea of the Big Bang, the time when everything in the universe is on top of everything else. It's kind of hard to imagine how you wouldn't get a Big Bang unless you literally had material being created out of nothing along the way, galaxies being formed out of nothing along the way. And so the expansion of the universe naturally leads you to the idea of the Big Bang. If I graphically put that on a diagram, like I have two galaxies right now at some time separated by some distance, and I run the universe in reverse, that dotted line shows you the trajectory of those two galaxies. And then when they come together, that's the time of the Big Bang. Now the dotted line there is essentially telling you how fast the universe is expanding now. We call that the Hubble's constant, and it literally is how far two objects are apart divided by how much space has expanded, or the redshift between the two objects. So if you can measure that, like what Hubble did, you can measure how old the universe is. So I thought this was a very interesting problem when I went off to Harvard to work on my PhD thesis. And here I am, 3 years, 11 months, and 4 days after starting at Harvard, showing my PhD supervisor, Bob Kirshner, my answer. And what answer did I get? Well, that the universe was about 14 billion years old. Now there's a complication. In this diagram, that line is straight. But the universe is full of stuff. It's full of gravity. And gravity will slow the universe down. It'll pull everything on the universe, will attract everything else, and you will expect the universe to slow down over time. So if that's true, then the Big Bang might not be 14 billion years ago from my measurement. Depending on how much stuff there is in the universe, it might only be, for example, 9 or 10 billion years old. And a 9 or 10 billion year old universe would be a problem, because we're pretty sure from the analysis of the oldest stars in the oldest stars in the universe are older than 12 billion years old. And we astronomers aren't too picky, but we do like the universe to be older than the things inside of it. So that was problem one. But there was an opportunity here, because if you think what happens in the past is going to be reflected on into the future. So imagine a universe that doesn't have much gravity in it. Well, that universe will just get bigger and bigger and bigger over time. It's a universe that goes on forever. It has an infinite future. On the other hand, a universe which is slowing down, well, it's a universe that would reach a maximum size. Gravity would completely slow the expansion of the universe down, and then the universe would go into reverse. And while both these universes start with a Big Bang, only the second one ends with a Gnab-Gib, which is the Big Bang backwards. So, as a review, The slowing down of the universe tells us how old we think the universe might be. It tells us the ultimate fate of the universe. And because space is curved, it turns out it tells us the shape and weight of the universe. So imagine you have a heavy universe, a universe heavy enough such the expansion will eventually stop and go into reverse. That's what we call a universe that is finite, and it's a universe that bends onto itself not in 3 dimensions, but in this 4th dimension that's related to time, which is at the very heart of general relativity. Now, people always complain to me that they struggle to visualize 4 dimensions, and that's okay. I do too. Indeed, I have never met a sane person who can visualize 4 dimensions. And trust me, you do not want to be one of the few people who can visualize 4 dimensions. So, a universe that's heavy bends onto itself. This is a universe that if I could do a triangle by, for example, sending a graduate student for 1 billion years, that's a little longer than the average thesis, that direction, and another one that direction, and we all get together after 1 billion years, traveling nearly the speed of light, and we say, okay, let's stop and let's measure the angles. We add them up, and they are greater than 180 degrees. We live in that universe. That's exactly what would happen if you do that experiment on Earth. If I send people out that direction, and they get several thousand kilometers apart, and we measure the angles, they add up to more than 180 degrees on Earth. Here locally, our little universe here on Earth, it's effectively flat because we can't see the curvature yet. But try a globe if you don't believe me. Get a piece of string and look at the angles on a globe, and you'll see that this is true. A universe which is light bends away from itself in the shape of a saddle where hyperbolic geometry works. This will have angles that add up to less than 180 degrees. And then there's the just right universe. That universe precariously balanced between the finite and the infinite. And it's just right also because people who study the time right after the Big Bang predict that the universe should have this geometry. Now, it turns out when you do this, everything in the universe that the universe might have in it, for example, photons, anything with energy, all add together to tell you the geometry. Okay? It's not just atoms, it's anything you can imagine in the universe contributes to this. So, imagine an experiment. And imagine an experiment where you could measure the Hubble's constant, or how fast the universe is expanding, back in time. How would you do this? Instead of just looking at nearby galaxies, look at really, really distant galaxies. Galaxies so far away that their light takes billions of years to reach us. Then you're looking back into time. If the universe has almost nothing in it, then the expansion rate in the past will be the same as the present. On the other hand, there is this dividing line. A dividing line which is where the universe is slowing down so much that we know in the future the universe will stop expanding and go into reverse. That's the finite universe. On the other side of that dividing line, gravity loses. We have a universe which is infinite that will expand forever. In 1994, circumstances, as I was leaving Harvard and moving to Australia, presented themselves where I thought we had the opportunity to undertake the experiment to look back in time. And those things were the form of knowledge, and new technology. The new knowledge came from understanding these objects known as Type 1a supernovae. To understand what a Type 1a supernova is, let's first review the life of our sun. Our sun formed 4.6 billion years ago, and in about 5 or 6 billion years, it's going to run out of hydrogen in its core, it's going to expand, destroy the Earth, and we're going to collapse down to a tiny little ball of gas known as a white dwarf star, about the size of the Earth, but the mass of the sun. Now imagine our sun was instead formed not as a single star, but as a binary. So the complicated life of a binary star is shown in this movie. So it turns out when the first star gets big, it will start transferring material to the second star. And that's because the first star would be a little bit more massive than the second star. Eventually, that first star that was transferring its mass to the other star turn into a white dwarf. It will form one of these beautiful objects known as a planetary nebula. Meanwhile, the second star will be chewing through its hydrogen, and at some point, even though it has a bunch of extra, it will start to get big, and it will start dumping material back onto the first star, the white dwarf star, making it become heavier and heavier and heavier, till it reaches a critical point, 1.38 times the mass of our sun, where it becomes the universe's largest thermonuclear bomb. A thermonuclear bomb not the size of a refrigerator, but the size of a sun, or even bigger than our sun. These things are amazingly bright. They're about 5 billion times brighter than our sun, so they're almost as bright as an entire galaxy. They take 20 days to reach their maximum brightness, and then they fade away into oblivion. But in the process, they produce 2/3 of the universe's iron. So the little bit of iron, normally when I'm in a room and has a lot of iron in it, this one not so much, but the little bit of iron that is in this room, 2/3 of it came from these exploding stars. Now, the piece of information that came from this was a group that I worked with in doing my thesis down in Chile, known as the Tololo supernova search. They were out looking at these objects, and they realized that there was a pattern. They realized that they weren't all the same brightness as had been previously thought, but rather some objects produced a little bit of iron and were not nearly as bright, but they rose and fell quickly. And the objects that produced a lot of iron were much brighter, and they rose and fell more slowly. And we more or less understand why that occurs phenomenologically. We're not exactly sure why the explosions are different. But with this new information, they were able to go out and make their own measurement of the expansion of the universe. And Mario Hamwi from that team, who was a friend of mine, came up and showed me his diagram. And these are all of his objects plotted up on a line, and what I first noticed is, wow, those objects are all exactly on the line, which means they were much more accurate measurements of distance than the things I had used during my PhD thesis. Fortunately, this was after my PhD thesis had been put in. But I got very excited because these guys I knew had discovered 29 of these objects, and we could use these as the fundamental basis of measuring distances, not just in the nearby universe, but in the very distant universe, because these things were so bright. And that's where the second thing that happened, technology. The new technology came in the form of 10-meter telescopes, Keck, eventually the VLT, but the Keck telescopes were the first telescopes powerful enough to reliably measure redshifts of these distant objects. But we had to find them, and it turns out that required another piece of technology, one that most of you have benefited from one way or another, which are large format digital imaging devices. Those came out of the military and were first brought into large-scale use by astronomers, and we all benefit from them one way or another with our digital cameras. So in 1994, the Keck telescopes came online. The Type 1a supernovae were shown to be useful distance indicators, and large format, the first 4-megapixel digital devices came online, shown here. So 4 megapixel, well, my iPhone's 8 megapixel, but this was 1994, where my iPhone now is, a much more powerful computer than we had access to then, and the average disk drive we had back then was a gigabyte. And of course, my iPhone has 32 gigabytes in it. That's like 32 computers worth. So it was a different world back then. And so these things came together for us to form what is known as the high redshift supernova team. Now, good ideas like this were not just us. It was actually two teams. One formed out of Berkeley by Saul Perlmutter. They had actually been working on finding these distant supernovae since 1988. We used to make fun of them because we didn't think they knew what they were doing with them. But once we realized that the technology had come for them to find it, and that the knowledge had come of how to use them, then it became a very obvious experiment to do. And so We had very different philosophies. They were from a group that worked in a particle physics background, very hierarchical, very much not invented here. Everything they did was done by their team from scratch, forget about what anyone had done for the previous 100 years. We were a very scrappy team with no money. I had $8,000 to spend on this project, which is how much we spent. That was mainly travel. They had many millions. That being said, it was a very good competition, and we did bring a lot to each other's experiments, and it was very important to have that competition. So the challenge for me was to write software to dig through roughly 1,000 of images like this in a period of a few hours with the technology of the day. So we would take roughly 50 gigabytes worth of data. Doesn't seem like that much now, but when you have 1 gigabyte hard drives and Pentium 120 megahertz computers, it was a lot of data. And the challenge was to find in these thousands of galaxies the supernovae, which are very rare. They only happen every 250 years or so. So you have to look at many hundreds of thousands of galaxies in a night to have the chance of finding one. So to show you the idea, I'll show you one of these exploding stars. In the middle there's a little star to the side of the galaxy. How did we know that was an exploding star? Well, we took not one images, we took two. And so the software I had to write had to process all this data, align it up to very high precision, subtract it, and then see the new objects. And that software was barely adequate, but it did what it needed to do, but it needed a lot of help. In this particular case, you can see in a period of 3 weeks, nothing has become something. That object, 5 billion years into the past. It exploded before the Earth was formed. So to give you a sense, I take you to Chile to one of our runs. Here we are on the CTIO 4-meter telescope. And this is the telescope that is equipped with this big digital camera. There's Greg Aldering from the other team, silhouetted in black because he's the bad guy. We used the same equipment because the same equipment, there was only a couple of places that had this equipment, this being the best place. As the sky goes by, we're trying to make sure that we get all the data just perfect because we only get 6 nights per year. Astronomers' telescopes are expensive, but we share. Everyone in the world shares the few telescopes. And so time is of the essence. My software is piling through this stuff, and it finds supernovae, but it also finds asteroids and junk. It's not perfect. So we have a sweatshop of astronomers looking at the little things it kicks up. And we have to work very quickly because 18 hours later in Hawaii, we have on board my colleagues at Keck who need to look at these objects and get a spectrum of it to see what their redshift is. And so Adam Rees and Alex Filippenko at Hawaii are there. And who's there at that telescope? No other than Saul Perlmutter, because of course he needs that piece of equipment as well. So very competitive teams. We used to see each other at the telescopes. We kept our finding charts with our discoveries to ourselves. And we even went out drinking occasionally after we were done observing. But it was a pretty intense competition. So that went on for 3 years. And after 3 years, I received an email in the end of November 1997 from Adam Rees, who was in the middle of doing his job of reducing some of the objects. And he said, well, have a look at this. And the diagram he sent me was essentially this one. And each supernova's measurement of how fast the universe is expanding is there as an error bar. Those error bars are 68%, or in other words, 2 out of 3 times the correct answer lies within the error bar. So you have to undertake a statistical analysis, which your brain is very good at doing by just sort of taking an average. So these objects are the objects that have been observed in Chile, and you can't really tell what's going on. You can't really see where they lie. But if you look at these distant objects, you note that every single one of them is above the gravity winds part of the diagram. That is, they're completely inconsistent with the universe, which is slowing down such that it will eventually stop expanding. And I have to admit I was a little depressed because I kind of liked the idea of a universe that has a beginning and an end. It seemed kind of nice. But I've soon realized that the universe does what it wants and it doesn't really care about how I feel about it. But then I got worried because I noticed that on average those objects did not lie in the yellow part of the diagram where I was expecting them to lie. Rather, they lie above the line in the part where the universe was expanding slower in the past and had sped up. Now, you do a statistical analysis and you say, well, how sure are you? It turns out when you do the number, you're 99.9% sure that those objects do not lie in the yellow part of the diagram. So it's 1,000 to 1. And on the basis of that, we wrote a paper, having done 5 months of checking the answer, because I have to admit, people say, did you have a eureka moment? And the answer is no. Adam's eureka moment was here in his notebook when he weighed the universe and found out the universe had negative mass. We didn't know what negative mass meant. We meant that the universe was speeding up rather than slowing down. But when I saw this, and when Adam saw this, we didn't say eureka. We said, oh, geez, what have we done wrong? And so there started this 5-month-long process of us working together and with the rest of the team, checking every aspect of the result any way you could, and finally just shrugging our shoulders and saying, well, that is what our data says, and we cannot think of any reason why it would be wrong. And sometimes in science, when you get the wrong answer, it's because the right answer was wrong. And that's what, in the end, we weren't sure about, but we felt that we needed to tell the world about it. Now, it turns out at the same time, Saul Perlmutter's team was struggling with the same problem. And in 1998, the two of our teams put out 2 papers, independent. We did not know about the other team's result until the very end when we were both writing. And we both essentially agreed exactly within a few percent on the answer. And this was noted at the time as being one of the few times that our teams had agreed about anything in public. And that is what the Nobel Prize was awarded for. And here in 2011 is the high-redshift supernova team, all 19 of us from 5 different continents, together for the first and only time. We had all known each other, we had all worked together, but we had never all been together as a team, except for at this point. And that shows the power of the internet. The internet was not so good in 1995, as I will attest to. It was 1 character per second between Chile and Australia, which made life very difficult. I never ever did not travel to Chile again. But it did allow this collaboration to work essentially 24/7, because we had members in Europe, Africa, Australia, and the United States. Also there, of course, was the other team. And here is Saul Perlmutter's team celebrating in Stockholm. And one of the things you need to realize, or I guess you truly appreciate, is that Nobel Prizes are celebrating the scientific discovery. And although they're giving to individuals, you have to realize that there's always, if not a team involved, there is a whole legacy of work done by science. And so ultimately the Nobel Prizes are a celebration of science, not of individuals. So if you ever win a Nobel Prize, I'm sure you're going to want to know what it's like, because no one ever told me. So when you win your Nobel Prize, they're going to show up and give you a car and a driver. Now, I believe that some of you will at least know the British TV show Top Gear. My driver's name was Stig. So he got us around the streets very quickly. For the front row here, go watch Top Gear. You'll understand what it means in the end. You get to meet the king of Sweden. In my case, the Swedes wanted to know, what does he say to you? In my case, he said, congratulations on behalf of the Swedish Academy, and thank you very much for the bottle of wine. Because I had sent through the Australian Embassy a bottle of my wine beforehand, suggested that he wait a couple years to drink it, but he had already done it in the week before I met him. Said it was very good. So that was very nice. And by the way, Pete, you described my winemaking as a hobby. If anyone from the Australian tax office is here, it is definitely not a hobby. If you come to Australia and give a colloquium at Mount Stromlo, you can be presented with a bottle of my wine. But it is sold out, largely speaking. You also, in my case, were given a princess. So this is Crown Princess Victoria, 6 months pregnant as it turned out. As I told my wife, I said, I look so glamorous with royalty on my arm. She wasn't that impressed with that statement, but she had the Swedish Prime Minister, so it wasn't all bad for her either. So we had a great time in Stockholm, and it was a real time as a team to celebrate. But I have to admit, I never thought we were going to win a Nobel Prize, because I had to ask myself the question, what is pushing on the universe? Now, we have a good guess, and that guess comes from Albert Einstein, and that thing he invented in 1917, the cosmological constant, really can fit the bill. It does exactly what we need it to be. But we don't really understand why it would be there. And because of that, and we're not exactly sure what it is, we give it a euphemism, which is called dark energy. Now, whenever you meet an astronomer and they use the word dark, dark is a euphemism for we don't understand. Okay? So dark means we don't really understand it, energy. Anyway, so dark energy, it turns out, if you do a detailed analysis to our data, requires a universe to be a mix of about 30% gravity that pulls and 70% stuff that makes gravity push this dark energy. So I have to admit, in 1998, when we published this result, I sort of figured it would be the end of my career. It was a very crazy thing. I thought we were going to be ridiculed. But rather, people were interested in this. It turned out it solved a lot of problems in cosmology. But the experimentalists wanted to test it out, and I wanted them to test it out. Now, several experiments were done. One of the first experiments was done in Australia, where they mapped out galaxies and how galaxies fill the local universe. And this is the map, 221,000 galaxies. And you can see that the galaxies of the universe make a foam structure. There's sort of a foam-like texture to that. And that foam-like texture is caused by gravity. Gravity that pulls matter together and forms galaxies in these big voids on sheets around voids. And it turns out the texture, the texture of that foam allows you to measure very accurately how much attractive gravity there is in the universe. And they were able, in 2001, to use this to realize that the amount of attractive gravity in the universe, they couldn't measure pushing gravity, just the attractive gravity, was roughly 30% of the amount necessary to make the universe geometrically flat, or just right, as I described. That's the way we weigh things. The universe weight is actually a density. We don't just weigh it because we don't know how big it is, but you can measure how much stuff there is in the universe. And the amount of stuff you need is 30% of that critical density where the universe stops expanding. There was a problem, one that it goes way back to Oort, among others, but that was 5 times more gravity than the atoms we can account for in the universe, leading to our second euphemism, dark matter. Now, dark matter is an unknown. We suspect it's some sort of undiscovered particle that, like a neutrino, can pass right through the Earth. And the way we detect things is through interactions. I mean, the reason you see me is because light is interacting with me, it bouncing off me and bouncing back to you. It then interacts with your eye and you detect it. But imagine you have something that travels right through me. Imagine light traveled right through me. Then you wouldn't see me. I would be invisible. And if this stuff can travel right through the Earth or anything, it would be almost impossible to detect. Our hope is that we will be able to detect it over the next decade or so. It's not guaranteed, but I think there's a reasonable chance through a variety of methods we might be able to detect it. But in the end, it has gravity just like atoms, but is essentially invisible. That's our best guess. Now, the other experiment that was done, also about 2001, was going out and looking at this map of the cosmic microwave background, that time right after the Big Bang. It turns out that what you're looking here is essentially sound waves, or think of it as like at the time of the Big Bang, we threw a bunch of gravel into the universe, and the waves rippled through the universe, and we took a snapshot of the universe 380,000 years later. And so those sound waves have a characteristic scale, which is how long the universe is expanding times the speed of sound. And those sound waves, because the universe is expanding, the sound waves get expanded with the universe. And through theory, we're pretty sure that those sound waves should be almost exactly 450,000 light years long. So we have a ruler. We have a ruler saying that's 450,000 light years long, and that's how big it appears. Now, the further away an object is, the smaller it appears, to a point. What happens when the universe is expanding is the expansion of the universe bends the light. And so in our universe, things get smaller, and then they start to get bigger again, because the entire universe acts as a giant magnifying glass. That we can figure out. It turns out very easy to calculate how that affects things. But there's another effect, which is the curvature of space. And so if the universe is bent, it acts as another magnifying lens, and not dissimilar to how a mirror distorts things that you see in it. The universe and the curvature of the universe can distort things. And so by seeing how big those sound waves appear, you can measure very precisely the curvature or lack thereof in the universe. Show you how it works. Here's 3 different types of the universe. We have a universe that is light, geometrically open. Then objects appear small. That is, that's like looking at a mirror on your car where it's a convex mirror that makes things appear smaller. Of course, if the universe is just right, then there is no effect at all, and you get sort of a in-between size. And then finally, if you have the mirror bent onto itself, that's like a convex lens, that magnifies the size of things. And so the measurements then turned out they look exactly the just right size. In total, if you do the measurement, the universe is within 1% of being exactly just right. Now remember, the amount of stuff in the universe determines if you don't have much stuff, you're open, if you're just right, you're flat, if you have more stuff, you're closed. But any type of matter, including stuff that makes the universe speed up or slow down, counts towards making the universe's shape. So if we add up all types of matter, they adds up to 100%, and we know 30% of it is the stuff that makes gravity pull. So doing some subtraction, we have 100% all matter, 30% attractive, leaving us with 70% mystery matter. The same mystery matter we need to speed the universe up in the form of this dark energy. So where does this leave us? Well, it leaves us with a bit of a mess. It leaves us with a universe of which only 5% of the universe is the stuff we know and love here on Earth, the atoms that we're made out of. The other 95% is in the form of dark matter and dark energy. Now you might be saying, now hold on it. If you got to invent 95% of the universe, doesn't it just mean you don't know what you're doing? And that would be a perfectly reasonable explanation, and sort of one I feel quite often. But the reality is that this model of the universe, which has been around since 1998, has been able to predict in advance every measurement we have been able to make of the universe thus far. And that comes to the notion of what is reality. Reality, like it or not, is a set of ideas that predict what you measure or observe in the universe. Nothing more, nothing less. Our view of reality changes as we gain more and more information. Same way, Newton's laws made a lot of sense until Einstein came along, but that version changes. So I can't guarantee this is exactly right how we describe it, but in the same way that Newton's laws were not exactly right, but we still use them, I think that this model of the universe will last into the future, even if we get a more sophisticated explanation in the future to explain it. All right, so let's talk a little bit about the future. So the future of science is always based on having better and better technology. Here in Europe, you guys are embarking on building an extremely large telescope, a telescope more than 30 meters in diameter. You can see how big this one in the Atacama Desert, which you're hoping to start here in the next few months. Australia is hoping to join your efforts, but my efforts at convincing my government have not been too successful as of yet, but we'll keep trying. And so this type of telescope will allow us to look back further and farther and make new discoveries. I can't tell you exactly what the discoveries will be. That's the point of doing research, or in the words of Einstein, if we knew what we were doing, we wouldn't be called research. And those are very true words. But that's not the only technology. We have new radio telescopes. Here near Groningen, you have home of the LOFAR telescope, which is a new pathfinder for the square kilometer array. In Australia, we also, in the very obscure region of Western Australia, in the middle of nowhere, we have our own pathfinder, which is very similar to your LOFAR, not quite as fancy, but it's in a more pristine site. We also have there a more conventional looking radio telescope, and these are all going to help the Netherlands, Australia, England, Canada. Oh, don't need cheesy music. Help us build this new generation telescope called the Square Kilometer Array. And again, the technology there and the development will open up radio astronomy to a place that we haven't been able to do it before. And so people always wonder, you know, why do we spend money on astronomy like this? These are expensive, billion-dollar facilities. And what we do is interesting, but the question is why we spend so much money. But in Australia, one of my colleagues, John O'Sullivan, who came here to Astron just down the road, was looking for evaporating black holes, which he never found, went back to Australia and used what he learned in his radio astronomy career to invent Wi-Fi, something that every one of us uses. That is Australia's most valuable invention. The politicians say, well, what are you going to do for us next? And the answer is, I don't know, but I would like to just have the return on what we've already given you, and we'll be fine. Thank you very much. You know, at CERN, the Large Hadron Collider, $8 billion, or 8 billion euros, but they invented the World Wide Web, which is $1 trillion a year now industry. The returns from doing this research, which you can't predict in advance, is inevitably, and my wife is a very dry economist, inevitably is shown to be incredibly valuable, one of the highest returns of investment that government can make, even though you can't guess what it is in advance. And that's why we do it. It's interesting, and it turns out it's actually worth a lot. So what's the future of the universe? Well, it turns out that we're in a battle between dark matter, which if you think is probably something like an atom, so it's dark matter and atoms together. And as the space expands, the density of this stuff drops, because imagine you have an atom in a box, the box gets bigger as space expands, and that means the amount of stuff per cubic meter drops away in time. But think about dark energy. Dark energy is part of space itself. Its density stays the same because as space gets bigger, this stuff gets created along with the expansion of space. So over time, you end up, if you look back in time or look forward in time, you end up with the balance of the universe changing. There's actually a battle for domination of the universe where the dark matter and atoms are battling in sort of a wrestling match for who controls the universe. Dark energy pushing, dark matter and atoms pulling. But sadly, 6 billion years ago, dark energy won the battle. And once dark energy wins the battle, it can make the universe, it pushes the universe apart, making it bigger, meaning its density stays the same and dark matter becomes weaker. So the more dark energy pushes, the stronger it gets compared to dark matter. And so we're essentially in a phase where the universe will start exponentially expanding. Essentially, the rate of expansion depends on how big it is in the future, meaning that the universe is going to expand faster and faster over time. Eventually, the creation of space will happen so quickly that it will exceed the ability for light to travel between objects we can currently see. Think of it this way. You got a galaxy, it lets a photon off, it's traveling through space towards us, but space is being created as the photon travels faster than the photon can get to us. Now remember, these objects aren't moving away from us at faster than the speed of light, it's space being created. And this is going to lead to, essentially, in the future, an island universe. Not an empty universe, an island universe. And that's because that's the density of dark energy. It's not very dense. The density of the Earth is about that. So we are 30 orders of magnitude more dense in this room, in Earth, than the density of dark energy. But remember all that empty space? I told you how much empty space there was between us and the nearest star. But then go between us and the nearest galaxy, and us and even the further galaxies. Eventually there's a place where dark energy is more dense than the average density of the universe. And that's the part that will eventually escape. In our own part of the universe, out to the nearest couple galaxies or so, attractive gravity is stronger than dark energy and has already won the battle of the universe. It stopped our part of the universe from expanding 13.5 billion years ago. That's why the Earth is here, is because our part of the universe gravity has already beaten this dark energy and allowed us to collapse. So in our little sphere of material, where the density is higher than dark energy, we will be safe from dark energy, because that part of the universe isn't expanding. But the rest, well, the rest will be history. So in the future, we'll look on to a galaxy that's a bit different than what we live in now. The Andromeda spiral will merge, as probably a couple other galaxies will merge, and we'll live in some super galaxy with, hundreds of billions of stars, more than we have now. But then we will look out, and we will look out into nothingness, because every other galaxy that has not merged into our super galaxy will be so far away that its light will not reach us. This is already happening today. When I showed you that picture of the deepest image from the Hubble Space Telescope, the galaxies in that image, the light that is traveling from those galaxies right now will never reach us in the future. And so in the distant future, there's not going to be a lot to see. We will see stars, but no galaxies. We will look out into an empty universe. Now the reality is, we don't really understand dark energy very well, and so if you were a theorist, you could make up any future for the universe you want. Because you can make dark energy disappear for, like that. You can make it change. You can do anything you want to it. However, one thing I am pretty sure of is that unless this dark energy goes away, and goes away very quickly, we are likely to live in a universe that at an ever-increasing rate will expand, fade away, and leave yours truly and my colleagues who study the distant universe unemployed, because we'll have nothing left to look at. Thank you very much.
Well, thanks very much, Brian, for a very fascinating lecture and an excellent presentation of the expanding universe. We have some time for questions. Now, originally we thought that people would be able to move forward after questions here. So we're going to ask some of these people to move forward, get out of the way, so that people who want to ask questions can come forward to the microphones. Just leave a little corridor for people to come. So who can I ask to ask the first question?
The first one's always the hard one.
Yeah.
Moet hier zitten hoor. Is die vrij?
Try to get to the microphone, or here is a microphone waiting for you. Use that one.
So this is probably going to be a stupid question.
There's no stupid questions.
Right. I understand that in the context of general relativity, space is bending
Yep.
right? And with the expansion of the universe, space is created.
Yes. Space is being essentially created, yes.
So there's new space
Yes.
between objects. No?
Yes, between objects where gravity is, I mean, we're not, no space is being created between us. And that's because this part of the universe isn't expanding. But between us and distant galaxies, yes, space is being created.
So is there ontologically not a difference between space bending and space created? New space being created.
It's slightly different. It's analogous to, let's just think of a sheet of rubber with a grid on it. I can stretch it or I can poke it. And so they're related to each other, but they are slightly different manifestations. It's essentially how you're mapping space over time. And one is, everything getting bigger and further apart, and one is distortion, where everything more or less stays the same size, but you distort where things are. So essentially, if the way to think about it is, imagine I'm a piece of light and I got to travel from A to B. If I distort space, then I sort of do this kind of weird roundabout pattern. If I stretch space, I just have to travel longer to get from point A to B. So it's very analogous to that rubber sheet.
All right, thank you.
Yep.
Yeah.
Who else? There's a question there. Is it easier for you to move forward, or here's a microphone coming towards you?
It's okay.
So how do we know that dark energy stays constant with time as with the expansion of space? How do we know that its density stays the same?
So that's a very good question, and that is a billion-dollar question, it turns out, because that's about how much money is being spent on answering that question right now. So if you were to have dark energy change, let's say its density changed back in time, then it turns out that changes how much it makes gravity push. That means that as we measure how fast the universe is expanding back in time, you will get a subtly different answer if the density of dark energy is changing back in time. So at present, we know that the density of dark energy over the last 10 billion years or so has not changed by more than about 10 or 15%. Our hope with modern experiments, with the next generation, is we'll be able to test that to 1%. And the hope is that if it is changing, then we can rule out Einstein's very simple explanation, and then it ends up being probably a particle physics explanation, something like the Higgs boson, but a different particle that would be changing over time. Its field would be changing as that particle evolves with the universe. So it is a big question, but it does turns out it affects how the universe expands over time.
Okay. And you talked about this super galaxy, which everything would turn to eventually. Will the super galaxy stay forever, or will eventually space expand so far that not even molecular bonds will be able to withstand the expansion of space?
Yeah, because well, it depends exactly what dark energy is, but let's do the simple explanation that Einstein is correct. Then, the super galaxy isn't expanding. It's just sitting there. But the process of evaporation, so you can think it's made up of millions of stars, and just like if I leave a glass of water out, the motion of the molecules, occasionally one, is able to break out in a way, and you actually lose water over time. The supergalaxy will have stars that get thrown out because they interact with another star and get more than the escape velocity. So over time, the supergalaxy will evaporate until you get down to a few stars, in which case that process won't happen anymore. In the very, very distant future, it's hard to know exactly what will happen. We're suspicious that things like protons may decay eventually. So at some point, it may be that even the stars that are left, or their remnants, will start to decay, and you'll end up with literally nothing. But that's not trillions of years. That is trillions upon trillions upon trillions upon trillions of years in the future. So it's a very bleak end for the universe. There are some more exciting ends to the universe, which I haven't told you about. Dark energy could be getting stronger and more dense over time. And that ends up giving us the opportunity for a new Big Bang as the density of the universe goes to infinity in the future. We call that the Big Rip, and that rips everything apart even at the to the subatomic level. But I would say that's not a likely outcome for what we know of the universe, but it's not ruled out.
Okay, thank you very much.
Yep.
The dark energy, is that a fundamental force, or has it nothing to do with, the four forces which I think we happen to understand?
Well, right now we have an explanation which dark energy is, it really acts via gravity. So the idea is that it's not an extra force, it's just energy that through gravity, gravity works on it through through the normal equations of general relativity. And it's the fact that it's spread thinly across the universe, or evenly across the universe, it turns out, that makes gravity want to make it push rather than pull. Now, of course, we don't know what dark energy is, and so people are playing around for explanations of it being a new type of force or something else. There's about 8,000 different theories right now for what dark energy is. Most people would guess that none of them are correct, but maybe one of them is correct, but there's no real way to tell them apart. So at present, the current model is it's just gravity, not an extra force, but I can't say that's absolutely right, but it seems to more or less, it certainly predicts everything we see, just treating it as gravity.
Anyone else? Sorry, at the back.
Yeah.
Thank you very much for your lecture. You touched upon it briefly in your lecture, and I was wondering, you explained shortly that where Earth sits in the universe, as you put it, is maybe not a very popular place to be. But I was wondering, why is that? Whenever you have the measures and when you had the pictures of radio measures of the universe, we could always see that we kind of are in the middle.
Yeah.
Can you shortly expand on why?
Well, so we certainly are in the middle of our own universe, sort of by definition. And we look out in all directions, and I can see 13.8 billion years that way, and I can see 13.8 billion years that way. It's really interesting, though, if I look at the stuff 13.8 billion years that way, and I compare it to the stuff that's 13.8 billion years that way, it looks essentially identical, even though that stuff can't see that stuff. So there's no way for it to have equilibrated, and that's one of the mysteries of why we think there's something called inflation that happened in the universe. But as near as we can tell, the Earth is in a kind of normal average galaxy, in kind of a normal average part of the universe, and that any other civilization on a planet with another planet, somewhere in the universe, would probably see a universe that looks very, very similar to ours. That's the evidence, is that we're not in a special place in the universe. We really are in a place that looks like every other place. And just remember that when we look at the cosmic microwave background, 13.8 billion years, and we see a little bump of hot stuff, when whatever that will have formed a galaxy and formed eventually planets, when they look in our direction, they see us as we were 13.8 billion years, and of course we're just a hot bump as well back then. So we get to see each other in our infancy, and everyone seems to see more or less the same thing as near as we can tell. Yeah.
Okay, maybe final question here then. Time running out. Maybe you can use this microphone.
You can use this one.
Yeah.
Excuse me about my voice. Thank you very much for your great expectations about the universe and the world. But my question is, what about mankind? In this century, I believe mankind will become a cyber mankind, and that could be the end of the life of Earth within the century. Yes.
So this is actually, it's kind of an interesting question because humanity has gained more and more knowledge. There's 7 billion people on planet Earth now. There's going to be 10. Our knowledge is exponentially growing. And the question is, where is it all going to end up? And I don't know. I share maybe not quite the same concern you do, but a related concern is that will humanity be able to sustain itself over the next couple hundred years and use our knowledge in a way that keeps us from exponentially growing out of control and essentially having a crash of a population like rabbits do? That's a big question. And how we actually crash, there's a million ways you can think of it. So eventually, 800 million years from now, our sun is going to die, or it's not going to die, it's going to be hot enough to boil off the Earth's oceans. So we got about 800 million years to make sure that we want to live forever. But the evidence is that it's not easy to live forever because let's assume in the 100 billion other solar systems around in our own galaxy that there's another human-like, or we'll just say intelligent species. Well, if they were formed 1 billion years ago, they'd have 1 billion years to get out, and once you can move from your planet to another planet, then that means you can travel between, and you will exponentially fill the galaxy. Now, I personally am unconvinced that UFOs have been seen involving aliens. I personally agree there's a lot of UFOs out there, but probably not many that involve aliens. This is known as Fermi's paradox. If humanity has a future that goes on as an intelligent species for a long time, then it would appear that we are the first within our own galaxy that will be able to do this. And that made Fermi think that maybe we won't be able to do it. That's the other explanation, is that it's too hard. So, I don't know, that's kind of a sobering way to answer it, but I do share your concern about our future. Thank you.
Okay, I think we should end this discussion. Before inviting you all to the reception downstairs, there are a few things I want to say to Brian, and also give him a few things. In the first place, here is a little book with Dutch literature translated into English. This is from the Studium Generale people. It's Harry Mulisch, The Discovery of Heaven. A very well-known book that is very appropriate, I think, for this particular thing. There is a book here which is by myself, actually. It's a meeting, proceedings on Kapteyn. As maybe some people know, I'm writing a biography of Kapteyn, which will be ready by the end of the year. I'll send you a copy of it. But this, in any case, is a symposium about Kapteyn. And finally, we have for the Kapteyn Lecturer a special medal with an engravement of the date and the title and your name, which I'm very happy to present you. Thank you very, very much again for coming to Groningen. You had to be in the Netherlands. We were fortunate to let you, you were able to come a few days earlier. We really enjoyed your fantastic talk this evening. All the best, and thanks very much.